Welcome to Blue Pen Land. So here's the question, right? This bullet is going to stick in this block of wood. We all know that this block of wood is going to be going slower, but it has more mass, right? And so momentum is conserved. The question here is the kinetic energy conserved? Do we have the same amount of kinetic energy that is small bullet going fast versus big bullet and block combo going slowly? That's the key question here. Do these have the same kinetic energy? Well, to answer that, we got to figure out what the velocity is here, right? So what's that velocity? Okay, so let's just do the momentum thing, right? So 0.012 times 351 plus 0. Let's assume that this thing's not moving, right? Equals, oh, what's the mass here? 3.215 plus 0.012. That's a 7, that's a 2, that's a 2. 3 okay, so this mass is 3.227. Okay, so that is 3.227 times V. And let's solve for V here. So 0.012 times 351 divided by 3.227. And I get that the velocity is a humble 1.305237 meters per second approximately, right? I'm trying to be really accurate here so that we're not off because of, rounding or something like that, right? All right, now let's figure out the kinetic energy before and after and see if they're the same. So this kinetic energy in general is, what, 1/2 AT squared? Geez, what am I doing? 1/2 mv squared. Wow, look at that. Isn't that funny? Where did that come out of my brain? I'm just daydreaming for one moment. There he is. So it's 1/2 mv squared, right? Okay, so we're going to go, the kinetic energy is 1/2 0.012 times 351 squared. All right, here we go. 0.5 times 0.012 times 351 squared. Well, that's a lot of energy. That's 739.206 joules. Again, being, as accurate as we can, right? And keep in mind that an airsoft gun is a few, maybe 1/10 of a joule, or a joule. A really hot one would be maybe a joule. This bullet is 739 joules, right? That would hurt. Okay, so let's see. The kinetic energy of this is 1/2 3.227 times 1.305237 squared. And of course, I'm just going to use the number that's in my calculator. So 0.5 times 3.227 times that number with all of its TI precision squared. And I get that the energy is 2.75 roughly joules, right? So you're like, oh my gosh, energy is not conserved. Well, no, that's not true. Energy is also conserved, but kinetic energy is not conserved. So some of this kinetic energy, in fact, about 736 joules, almost all of it, right, turned into something else. And the answer to the mystery here is that it turns into heat, right? Bullets can actually just melt. They're made of lead. It's not too hard to melt them. So sometimes, they'll melt in collisions. So yeah, a whole lot of heat got generated ultimately, right, of that bullet ripping into that block and all that friction. So this is what we would call an inelastic collision. Okay? In an inelastic collision, kinetic energy is not conserved. Now rest assured, momentum is always conserved. This is always going to work. Okay? But you almost never can say that the kinetic energy before equals the kinetic energy after. There are some rare exceptions to this. Okay? We pretend like collisions are elastic, but it's very hard to do so. An example of an elastic collision, one where the kinetic energy before and after is the same, would be the collision of a air molecule with maybe a wall or the side of a glass bottle or something like that. And that's, of course, because the air molecules are traveling through a vacuum, so there's no air friction. And that's a funny thing, right? And then that collision is not really a collision. It's just that stores the energy in it, some sort of electric repulsion, and gives it back. Okay. Anyway, yeah, that's all we can say about this, I think.